Imagine standing on a skateboard, feeling the smooth surface beneath your feet, ready for a gentle push. You know what will happen next, right? The laws of physics are on your side. Your friend gives you a gentle push, and you roll forward, just as you'd expect. The force moves you in the direction it's applied, and you glide across the floor. This is Newton's law of motion. An object moves in the direction it is pushed. It's a rule that governs everything from falling apples to orbiting planets, and it's so reliable that we rarely question it. But what if, somewhere out in the vast cosmos, the rules we take for granted are bent, twisted, or even broken? What if the universe has surprises that defy our everyday experience? Imagine pushing that skateboard, but instead of rolling away, it accelerates backward, straight towards you. It's as if the universe is playing a trick, flipping the script on everything you know. Welcome to the world of negative mass. A concept so strange, it almost sounds like science fiction, but it's a real idea in physics, and it challenges our deepest understanding of how matter behaves. Negative mass flips our understanding of mass and gravity on its head. Instead of following the rules, it does the opposite. It's as if gravity itself gets confused, and the normal push and pull of the universe are reversed. Normally, positive mass is attracted to other mass, like how the Earth pulls you down, or how planets orbit the sun. But negative mass would be repelled by positive mass, and even by itself. It's like two magnets with the same pole facing each other, always pushing away. Drop an apple with negative mass, and instead of falling, it would shoot upward, defying gravity as if it were allergic to the ground. The very idea seems to break the rules of reality. For years, negative mass was just a mathematical curiosity, a ghostly presence in the equations of physics, haunting the chalkboards of theorists, but never seen in the real world. But now, recent scientific breakthroughs have brought this wild concept out of the shadows. Physicists have started to create and observe conditions where negative mass-like behavior actually appears in the lab. Using ultra-cold atoms in carefully controlled environments, scientists have managed to coax matter into behaving as if it has negative mass. These experiments are opening a new frontier in physics where the impossible becomes possible. This journey into the unknown promises to challenge everything we know about reality, from the tiniest particles to the largest galaxies. It could even help us unlock the mysteries of dark energy and the fate of the universe itself. The quest to understand negative mass has just begun. As scientists push the boundaries of knowledge, we're all along for the ride, and it promises to be a wild, mind-bending adventure into the heart of the unknown. Creating negative mass isn't simple. Scientists at Washington State University, led by Michael Forbes and Peter Engels, embarked on this challenge. They used rubidium, a silvery metal, transforming it into a Bose-Einstein condensate, a state of matter achieved at near absolute zero. Cooling rubidium atoms with lasers and magnetic fields, they created a superfluid, a liquid that flows without friction. In this state, atoms behave collectively, like a single superatom. This superfluid was the perfect stage for testing the limits of physics. The scientists had crafted a substance governed by quantum mechanics, ready to explore new physics. They prepared their canvas, an exotic state of matter, to see if these atoms would push back in unexpected ways. The cosmic kitchen had served its first course, and the main event was about to begin. With their superfluid finally prepared after days of meticulous work, anticipation filled the air. The team of physicists at Washington State University knew they were on the verge of something extraordinary, an experiment that could challenge the very foundations of physics. Every detail mattered as the scientists carefully set up their equipment, calibrating each instrument with precision. The room was filled with a quiet intensity, as if everyone present understood the significance of the moment. At the heart of their setup was a Bose-Einstein condensate, a state of matter so cold and delicate that it could only exist under the most controlled conditions. They held this fragile cloud of rubidium atoms in a laser trap, a container made entirely of intersecting beams of light, suspending the atoms in a near-perfect vacuum. The next step was crucial. By manipulating the lasers, the scientists planned to nudge the atoms and observe how they would respond. Would the atoms behave as expected, following Newton's time-tested laws of motion, or would they reveal something entirely new? The team watched intently, their eyes fixed on the monitors and instruments. The question lingered in the air. Could they witness a phenomenon that had only existed in theory until now? With a calculated move, the researchers switched off the laser trap. Instantly, the rubidium atoms began to expand outward, just as predicted. But this was only the beginning. Using a carefully timed pulse of lasers, they imparted a specific push to the atoms, altering their quantum spin and setting the stage for the unexpected. Then, something astonishing happened. Instead of moving forward as Newton's second law would dictate, some of the atoms accelerated backward, moving in the opposite direction of the applied force. It was as if the rules of physics had been momentarily rewritten. This bizarre behavior was the unmistakable signature of negative mass, a concept that had long been discussed in theoretical physics, but never before observed in the lab. For a fleeting moment, these atoms acted as if their mass was less than zero, defying our everyday understanding of how matter should behave. The effect was temporary, lasting only a short while, but it was undeniable. The data was clear, and the phenomenon was captured on camera and in measurements. The researchers had succeeded in creating a system that mimicked the properties of negative mass, opening a new window into the quantum world and its strange possibilities. What was once a theoretical curiosity had become a real observable phenomenon, one that could now be studied, measured, and perhaps even harnessed in the future. In that moment, the scientists glimpsed a bizarre new reality, one that challenges everything we thought we knew about the nature of push and pull, and invites us to imagine what other impossibilities might one day become real. Let's explore the strange and counterintuitive behavior of negative mass, a concept that challenges our everyday understanding of physics and reality itself. In a groundbreaking experiment, scientists observed atoms recoiling as if they had struck an invisible wall, even though no physical barrier was present. This bizarre reaction was the first clue that something extraordinary was happening. With negative mass, the rules of motion flip upside down. When a force is applied, instead of moving in the direction of the push, the object accelerates in the opposite direction. This is the exact reverse of what we experience with normal, positive mass. Imagine trying to push a box across a table, but instead of moving away from you, it slides toward you. A push becomes a pull, and a pull becomes a push. This is the strange world of negative mass. To picture this, think of a car with negative mass. If you step on the gas pedal, instead of speeding forward, the car would lurch backward, defying all your expectations about how vehicles should behave. In the lab, scientists used lasers to push on a cloud of atoms. Astonishingly, the atoms didn't move away from the laser's force. They accelerated in the opposite direction, as if they were being pulled instead of pushed. This behavior isn't just a scientific curiosity, it has profound implications for our understanding of the universe, offering a new model to explore the most extreme and mysterious aspects of physics, such as dark energy, exotic matter, and even the possibility of warp drives. It's important to note that the experiment didn't create true negative mass particles. Instead, scientists engineered a system where atoms behaved as if they had negative mass, using clever techniques to manipulate their environment and interactions. This engineered system acts as a sandbox for physicists, a safe and controlled environment where they can test wild ideas and theories about negative mass without the risks or unknowns of dealing with actual exotic matter. With this setup, researchers can now study the behavior of negative mass under a variety of conditions, refine their theoretical models, and make new predictions that could one day revolutionize our understanding of the cosmos. It's like having a wave pool in the lab, where scientists can create ripples, observe how these waves interact, and gain insights into the properties of this strange, anti-gravity-like substance. The possibilities for discovery are just beginning. Creating a liquid that defies motion laws is a scientific achievement with profound implications. This experiment provides a new tool to view the universe, simulating extreme phenomena on Earth. Like a flight simulator for cosmic exploration, it allows astrophysicists to recreate physics happening in distant, dense objects. Our understanding of the universe is incomplete, with theories breaking down in extreme environments. This experiment offers a chance to probe new physics, expanding human knowledge. It's a tool to experiment with space-time, potentially unlocking answers to age-old questions about the universe. This research tackles two major cosmology mysteries: Dark matter and dark energy. These entities make up 95% of the universe, yet remain unseen. The dark fluid hypothesis suggests they could be explained by a single fluid with negative mass. This fluid would be gravitationally repulsive, explaining the universe's expansion and galaxy formation. The Washington State University experiment allows scientists to study negative mass fluid behavior. They can test if it aligns with cosmic observations, providing a physical model to check the math. It's a step toward determining if this theory is a genuine description of reality. Negative mass opens the door to wormholes, hypothetical shortcuts through space-time. Wormholes could allow near-instantaneous travel between distant locations. However, they are predicted to be unstable, collapsing quickly. Negative mass could stabilize wormholes, acting as a cosmic scaffold. Some speculate supermassive black holes might be wormhole mouths. While highly theoretical, studying negative mass in the lab is a first step. Understanding its properties could one day lead to engineering cosmic shortcuts. Wormholes could also enable time travel, rooted in Einstein's relativity. Time dilation means time passes differently for observers in different conditions. A stable wormhole could create a time machine, connecting different points in time. This concept comes with paradoxes, like the grandfather paradox. Negative mass is needed to stabilize wormholes, making time travel possible. While beyond current technology, the laws of physics don't forbid it. Studying negative mass is a step toward mastering space and time. We stand at a pivotal moment in science, with negative mass moving from theory to lab. While far from building wormhole generators, this achievement shifts our ability to explore the universe. Scientists face challenges in sustaining and scaling the negative mass effect. Each success brings us closer to understanding its potential for future technologies. This research opens new avenues of inquiry, inspiring bigger questions. Could negative mass be harnessed for limitless energy or star travel? The journey from discovery to technology is unpredictable, but it ignites our imagination. The universe is filled with wonders, and the quest for knowledge is the most exciting adventure. The cosmos has shown us a new trick, and now, the real work begins.